Thank you. I'm going to talk about crystals for this affine algebra SLN hat. And I think this title is quite vague, partly because I wasn't exactly sure what I was going to talk about when I sent the title and abstract. But what I want to do is really discuss very explicit models for these crystals, as explicit as possible, some different models that exist, and how they're related. And again, as explicitly as possible. And I'm going to be more precise on what I mean by that later on. But I think it's a worthwhile goal. Much of what I'm going to talk about is actually expository. And there's some which button? This button. There's some notes to look at. Also, these slides are on my web page. It's not all in here. And I'm actually going to draw on quite a lot of sources here. So we'll try and credit the right people at the right times. And of course, I will also mention a few new results, so at least somewhat new. OK, so see if I remember. Got it. So here's an outline. I'm going to start with a little bit of motivation. This is a quick review of crystals, which, given the audience, is going to be very quick. Then I'm going to try and this is a strange title for a section, but I'm just going to try and explain what questions I'm trying to answer. That's what this is. Then I'm going to give two examples, one of which I claim I do fully understand. It's not my model. It's the Miwa crystal, in fact. And another one which I understand less well, which is the Monomial crystal of Nakajima. Then I'm going to, this whole section is essentially really elaborating on higher level generalizations of this Miwa crystal. In particular, this one I say I do understand is the crystal of Jimbo, Miwa, and Okado. And here I really claim it's very well understood. And in fact, I'll end with a bonus of how it's related to the Kyoto path model. Then I'm going to discuss some stuff that I think is less well understood and is in fact more recent. So these are some crystals. Very recently, it was at the beginning of the summer, a paper posted by Matthew Fayers, who constructed, this is at level 0, just models for lambda 0, but an infinite family of them. And all of which are parameterized by partitions. So it's something kind of new. And it's got a relationship with the monomial crystal, which is, I guess, due to me. And then I'm going to discuss maybe where this, I hope, will go, although I don't know. So let's get started. Nope. All right. So what's a crystal? Well, I'm not going to give any definition or anything. I'm going to give an example which just, I think, helps illustrate how I think about them. And the example is the adjoint representation of Sl3. And if you draw the representation, I think we all know it has 6 one-dimensional weight spaces and a 2-dimensional weight space in the middle. And the F1 operators, which I've drawn in blue, go in sort of this direction, and the F2 ones go in sort of this direction. And you can look at this and almost think you've drawn the whole representation as a graph. But you will find if you try and actually draw it, you have some problem in the middle. Because this is a 2-dimensional space. And there's sort of 4 distinguished one-dimensional spaces in the middle. There's the images of these 2 maps and the kernels of these 2 maps. And they don't match up. And so somehow there's 4 things you might want to use for dots in here, but you only should have 2 dots because it's only a 2-dimensional space. But you fix this by this wonderful observation of Kashiwara, that if you use the quantum group instead, and you sort of rescale the operators, and this is maybe, you do something more than just rescale them. You turn them into the Kashiwara operators. You let Q equal 0, and those 4 one-dimensional spaces match up exactly. And in fact, you can choose a basis so that these maps all just move from basis element to basis element, and that's your crystal. Great. Now, what's a model for a crystal? Well, a model for a crystal is, instead of going through all the representation theory and figuring out what the graph is, you draw the graph in some other way and notice that it's the right one. So in this example, you would do it by using the semi-standard Young tableau. These maps are defined combinatorially. You notice it's the same crystal you would have got out of the representation theory, and you say you've realized it. And this can be useful, because if the combinatorics is very nice, it can sometimes tell you stuff about the representation theory, or the other way around. In principle, it's possible. OK, that's it. We've reviewed crystals. I still don't remember which direction. Oh, Yeah, and I guess I just added this comment. When I say crystal, I mean this graph. And a lot of people mean you should have these three functions, weight and epsilon and phi as well. And for this talk, I'm not going to include those. And the reason is I'm always thinking about highest weight crystals. And you can recover these three things anyway. So I see no reason to write down how to recover them in every case. All right, so then I guess I'm doing SLN hat. So I should say what an SLN hat crystal is. I think we all know SLN hat is the custom algebra with this Dynkin diagram. And all you need to know that something is an SLN hat crystal is that if you, for SLN hat, I guess it's going to have n different colored edges, one for each node of the Dynkin diagram. And you just need to know that if you look at two edges at a time, it's either an SL3 crystal or an SL2 cross SL2 crystal. So these are what we're studying. All right, now I'm going to mention this infinity crystal. I think, well, let's just say it. So there are embeddings of crystals into larger crystals. So here's a larger SL3 crystal. This is 2 omega 2 plus omega 1, I guess. And if you just erase some of these edges, you see the crystal for the adjoint representation, the one I just drew. And so there's always a map from, if you have a larger sum of fundamental weights, there's always a map from the smaller crystal into the larger crystal, which is, the precise statement would be it's invariant under the ease. So if you try and go up in the small one, it's the same as trying to go up in the large one. And this really is algebraically part of the structure of the crystal, in that we know the crystal is coming because there's a canonical basis for UQ minus, and that the canonical basis for that projects onto a basis for each representation. So I feel if you're really going to combinatorially say you understand this structure of crystals, you should understand these embeddings as well. And you should also understand what happens in the limit. You should understand the crystal for all of U minus, which is some graph that looks like this in this case. So if you just take the limit, figure out all the edges that show up anywhere, you get this graph. OK, so that's the infinity crystal. And then I've already said this, so I'm going to go through very quickly. But what do I mean by understand? Well, at very least, I want a very explicit description of the vertices that show up in the crystal. And I don't want to do anything recursive, like say this is what the highest weight vertices are, and you just apply the operators and see what you get. I want something explicit. I want to explicitly understand these embeddings. So if I have a different model for the smaller crystals than the bigger one, I want to explicitly know how to push the elements of the smaller crystal into the bigger crystal. I want to explicitly understand the limit. That's all. So if I can do all of these things, I say I understand that model. I think no one can argue that it's not understood if these things are all understood. Oh, of course you need, yeah, that should be up here. Explicitly describe the vertex set and explicitly describe the operators to give the edges, yes. Somehow that's usually, no one even talks about it unless you can explicitly describe the edges. So that's always there for me already. All right, and then what do I mean when I said understand the relationship between two models? Again, what I want is an explicit description of the bijection. I mean, you know they're the same crystal, so there's a unique bijection between them that commutes with the operator, but I want to explicitly know it. And of course, yeah, and I want it to be better than saying recursively using the operators. And of course, what better means is always up for debate. So I won't necessarily give a definition of the word better. All right. Now let's draw some pictures. This is this is the first one, and this one I feel I truly understand. That's this Mizuo-Miura crystal. And maybe should put, oh yeah, I did put Hayashi in there too. Good. Mizuo-Miura Hayashi. And so the vertex, you start by defining operators on partitions. And I'm going to draw my partitions at this angle, which some people call the Russian notation. And so I'm going to call this the partition 7, 6, 6, 6, 5, 3, 2. Then I'm going to color it with 3 colors because I'm doing SL3 hat. And I'm just going to show you what F2 does. Once we know that, it's all fairly clear. What it does is add a 2-colored box. So for instance, maybe it does that, except somehow we need to decide which of the possible boxes we add. And the way you do that is you start looking at all possible ones you can add and putting a left bracket, and all ones you could possibly remove, put a right bracket, see what shows up, cancel the brackets where they cancel, that one would be added. That's the rule. Okay, and if you wanted to do F1, you would do the other thing. If you wanted to do E2 instead, I think I maybe even say this. Yeah, E2 would send this to 0 because you do the same string of brackets, but you look at the right brackets, and you want the first uncancelled right bracket. It doesn't exist, so it sends it to 0. Okay, so theorem due to, I guess, Isomorphism, Hayashi. Every connected component is a copy of B lambda 0 of this fundamental crystal. In particular, the subcrystal generated by the empty crystal is a model for one copy of this crystal. Now, at this point, I wouldn't say we understand it, because I haven't told you exactly which partitions show up in this crystal. However, in this case, it's known. So the subcrystal, so this single copy of B lambda 0, consists exactly of 3 regular partitions. And what does 3 regular mean? It means that there are not 3 rows, well, there are not 3 rows of the same length in this case. That's all. So this is not 3 regular, but if I did this, it would be 3 regular. So this one would be in the crystal. Okay, so model we understand. Now I would like to, an example. I'm going the wrong way, I think. No? Yeah, now I'm going the right way. Now I would like to give a model that I don't understand nearly as well. So this is Nakajima's monomial model. So what you do is you consider monomials in variables labeled by, Laurent monomials in variables labeled by your Dinkin diagram and integers. So for instance, you could have some product like this. I always like to do big examples. And I'm doing n equals 4 in this case instead of n equals 3, because not everything I'm going to be, well, I'll say why. And then so we define operators by a very similar rule. We put left brackets over monomials with a 1, so yik for all k. And left ones when I have negative powers of the monomial with an index I. So I'm doing f1, so, well, I think it's pretty clear. You get that string of brackets. And these are ordered in decreasing k. You look for the first uncancelled bracket, which I think in this case is going to turn out to be this one, and you multiply by this specified thing, which depends on k. All right, and it sends it to 0 otherwise. And this should say e. So e does the same thing, but multiplies by a different one. All right, and I don't even want to talk that much about it. I will just show you it happening. So in this case, look, this is the uncancelled bracket. I multiply by this ak. It expands as this product of 4 things. I simplify. Again, putting everything ordered from largest to smallest, because I might want to apply another operator. That's the rule. OK, theorem. The component generated by a dominant monomial is a highest weight crystal. Dominant means all exponents are positive, no negative exponents anywhere. This is provided n is even, and there's some parity condition on exactly what the dominant monomial is allowed to be. So these things can sort of be fixed. Well, at least this one can sort of be fixed. Some of this can sort of be fixed. But the way I presented it, you need some conditions here. But nonetheless, you get models for some highest weight crystals. And, oh yeah, other components aren't crystals. So you start with a random thing. It's not going to be a crystal at all necessarily. And I guess I wanted to mention that Hernandez and Nakajima have described, to some extent, at least many other components that are crystals. So there's something known about which components are crystals. I don't want to get into that. But what I do want to point out is that in particular, if you start with y00, 0, you get a copy of this b lambda 0, because that's really the only case I'm going to talk about. And this, in fact, holds for any n bigger than 3. You don't need to worry about n even here. This is always true. And I do not really feel I understand this crystal, because I don't know a good rule for checking if a given monomial is in this b lambda 0. The only way I know how to do it is to start trying to apply e's to it and see if I get back to y0. That's the best I know. Maybe some people know better, but I've asked David Hernandez, and he claims to not know better. So I claim Well, I mean, I understand many things about it, but I don't understand the crystal in total. I also don't know an explicit isomorphism with the Monomial crystal. Again, the best I know how to do is say, well, we know what the highest weight thing is on both sides, so there's a unique map. But that's the best I know. I do know an explicit isomorphism with one of these cases of the Thayer's crystals, which I think is, I will argue at the end that this is somehow, I don't know if it's progress to ever having an explicit isomorphism with the Monomial model, but it's progress to understanding why we don't have it and perhaps how they're related in some other sense. So, all right, so that's this Nakajima monomial model. Now what I want to do is, mostly because I can, not necessarily because it fits very, very well with everything else I want to do, but I want to really tell you some things about this multi-partition realization due to Jimbo, Monomial, Okado, and occasionally cited as Foda, Leclerc, Okado, Thibon, and Walsh. And I'm just going to, again, do this by examples. So I'm going to do level 4, so you should use 4 tuples of partitions. And they should be charged. Somehow we should have chosen a charge, which is a 4 tuple of residues mod 3, because I'm back at n equals 3. And what this multi-charge tells you is the color of the 4 vertices. Okay? And these are supposed to satisfy some sort of shifted containment condition. So what is that? That is that this partition here, here's I don't know whether to call these columns or diagonal, but these vertical strips of zeros. This vertical strip of 0 somehow matches up with this one. And so I shift this so that they agree, put it on top of that one. It should be contained inside it, which it is. This one should also be contained in this one. They're the same, so you don't have a shift. This one should be contained in here, which it is. And also, this one should be contained in here, which it is. So those are the conditions. So you should look at the set of all 4 tuples satisfying that condition. Then I'm going to just show you how F0 acts. So again, every time you see a removable box, put a right bracket. Every time you see an addable box, put a left bracket. We get some long string of brackets. Now, it looks like we should just use this string of brackets, cancel them, and move. And if we did that, in fact, what we would get is the tensor product crystal structure between these four things. But that's not what I want to do. And yeah, then the highest component would be called Kletchev multi-partitions, I think. So maybe I'll say that. But that's not what I want to do. I want to change the order of these brackets. And here's how I change them. I want to label these diagonals, this 0 diagonal that somehow went with this one. I'm going to call them both 0 diagonals. This one's also a 0 diagonal, and the third one over here would match up. So that's a 0 diagonal. And then I just want to count the diagonals. So this is -1, -2. Sorry, for some reason I count right to left these days. I don't know if that's a good idea or not, but I do it. So this is in fact -1, -2, and -3. This is 1, 2, 3. And the order you want on these brackets is lexicographically by the label of its diagonal and then left to right. So this one corresponds to a diagonal of, and decreasing in order of diagonals. So this one corresponds to a diagonal of 6, so it comes first. This is the leftmost one that corresponds to a diagonal of 3, so it comes second. You just go through the diagonal 3s, go through the diagonal 0s, go through the diagonal -3s. I think that's it. Look for the first uncancelled bracket. It's that one. So F0 would add that box. And that's the rule. OK. So what's true? Well, every component is a copy of B lambda, where lambda is lambda 0 plus lambda 1 plus lambda 2 plus lambda 1 plus lambda 2. These fundamental weights that are given by the colors of these corners. The so-called 3 regular multi-partitions form a single copy of this B lambda. Well, what does 3 regular mean in this case? It means that there are no 3 rows, again, that are all different colors and the same length. So now we could have rows that are the same length but also the same color because they are in different partitions. That wouldn't count. So we need all three different colorings to happen. So in this case, we have this, this, and this. So it's not 3 regular. So this, in fact, is not in the highest component, what I've just drawn. So it's not 3 regular. However, I say we understand this because we know what the highest component is. This 3 regular condition is extremely easy to check. It's good. OK. Now, next, embeddings. And I guess I should say what I'm about to say is all, in some sense, due to Ricky Jacquin, Lecouvé, I think, or some subset of them in a couple of papers. The only thing that could at all be attributed to me is that they didn't draw the pictures this way. So, all right. So what am I talking about? What I'm talking about is you should notice that this shifted containment condition means that these things are going to fit into some sort of 3-dimensional picture. So I'm going to move down to level 2, so only 2 tuples because the pictures got out of hand. So consider this tuple, again, with n3. And this corresponds to this 3-dimensional picture. And how does it correspond? This is a cyclic picture. So you see a copy of this partition 3, 1, 1. For some reason, I have my rows going straight up now. 3 times. And in between them, copies of 2, 2. So this 3, 1, 1 is this 3, 1, 1. And this 2, 2 is this 2, 2. Yeah, I guess some more things. And this shifted containment condition, you can see, is exactly the same thing as saying when I draw it like this fits inside here. And so I've put like this length 1 here is because the difference 1 minus 0 is 1. And 0 minus 1 is 2, is why this is shifted back by 2. It's all just determined by this highest weight. So instead of drawing tuples of partitions, you can draw a 3-dimensional picture, which is more difficult to draw, but somehow easier to look at, perhaps. And then the coloring of these gives a coloring of the 3-dimensional picture. But once I colored that, I realized it completely was not possible to look at. So what I'm going to do is only color the tops of the piles of boxes. And you can recover everything from knowing the tops of the piles of boxes, what color they are. OK. And oh yeah, and I guess you want to know which ones show up. And all that the condition is that if you want to be actually in this B lambda, you should have no 3 piles of the same height and differently colored. Again. OK, so now I want to understand these embeddings. And I'm just going to do it by showing you the embedding of this is B lambda 0 plus lambda 1, where this is an element of this B lambda 0 lambda 1. I'm going to tell you what it looks like in here. And what you do, and this, thank you, 2 typos. 2 lambda 0. Thank you. Hopefully. Either that or I mean lambda 0 plus 2 lambda 1. But what you should do is you should look at, notice before I was saying this 3-dimensional picture is determined by this 2 tuple of partitions, so that partition and this partition. You can also just read it at the other possible angle. And you see a 3 tuple of partitions. You see this partition would be 2, 1. You see a 3, 2. And you see a 1. And the way this embedding works, I guess I'm going to call this the dual n tuple of partitions, is that it keeps exactly the same dual n tuple of partitions. You simply do not change this, but draw the back wall of this 3-dimensional picture so that the highest weight is this highest weight, where you write the highest weight correctly, and see what happens. So what happens in this case, it just gets shifted like this. So I've put in, whereas before there was only one thing here, I've put in a second one. Because I'm allowed to have 3 partitions going this way, there should be more back wall there. You just shift, and you see what happens. And this is your element of the higher crystal. And this is, I mean, once you know this, it's not very hard to check. If I had explicitly described the crystal rule on this partitions, which I didn't, that that this commutes with the crystal operator, with the EIs. Okay, so, and let's just see what happens to a given thing. I did that, I shifted it, I now get a 3-tuple of partitions where, well, all that happened in this case was that these 2 rows got separated. And in general, it'll be considerably more complicated than this. Yes?
Was there a choice, you had these 3 black lines there?
Yeah.
1, 2, 3. Was there a choice that you started that your first one was, I mean, it's sort of cyclically repeats, but
yeah, you could.
The way that you decided to shift according to the lambda matters where you start your 1, 2, 3.
Well,
you started somewhere else.
What's going on is that these back walls have associated with them a color, which is the color of, if it was empty, if I removed everything, there would be the color visible on the floor just before I hit the wall. And that color is which fundamental weight that segment corresponds to.
But that's from the original 0, 1. But like this, you're embedding into 2 lambda 0 plus lambda 1.
Yeah, no, in the original 0, 1, that corresponds to a fundamental weight. So that back wall is somehow labeled by a fundamental weight. When I shift and make it the bigger one, I know which fundamental weight I'm adding in. So in this case, I added a lambda 0. So I should look for the part that's labeled by lambda 0 and make that longer. Right, so let's draw this. So the back wall originally was something like this. It had 1 step and then 2 steps. Yeah? And this is labeled with a 0, and this is labeled with a 1. And if I want to have 2 zeros, and so this should be here. If I want to have 2 zeros, I need to make this longer, and so on repeatedly. So that tells me which one to make longer. So that tells me.
Order it so like all your zeros are first and all of your ones, so you can always add. There's not a choice where to start.
That's right. Yeah, it's always labeled cyclically. Yeah. And of course, there's a symmetry. I could change my labels or something, but that would be just changing the crystal by some symmetry. Yeah. Okay. Everything else clear? Hopefully. Okay, so what was I saying? Yeah, I was saying that all that happened in this case was that these got split. In general, it does some much more complicated shuffle of the rows, but it keeps the set of rows exactly the same. So that's what happens. And that's just because it keeps the set of piles with their colorings exactly the same. Okay. Well, if you want to understand B infinity, then, well, in some sense, what I just said is you should just record this dual n-tuple of partitions. And that would record an element in B infinity because it's an element in any large enough crystal. But what people a little bit more accurately do is just record the piles of boxes. And this allows you to recreate this dual n-tuple, because if you know the heights and you know the colorings, you know which occur in which of that n-tuple. And you just record this pile of boxes. And then you might call it something like a multi-segment. And so this is, in fact, exactly how you go between these n-tuples of partitions and multi-segments, at least in the sense that Ariki, Jacquin, Lecouvet are using them in their paper, which is the same way that Monaco is using them. I'm not 100% convinced there's not other things people call multi-partitions. And then you can directly define the crystal operators on these multi-partitions, and it's much the same rule. You order them from highest to lowest, you put brackets, you cancel them, and it all works out. All right. Now I really say we understand this model. All right, relation to the Kyoto path model. This is just a very quick aside. Aperiodic, yes, I believe so. Yes, that's right. So aperiodic is the condition of not having 3 different colored ones of the same height, which is exactly the condition. Yes, these are those ones. Yeah. Unfortunately, I've read about these in these Jacquin, Lecouvet, and Ariki papers, but I believe they're the same. Okay, so how do you get to the path model? I need to color the whole thing, and this time, instead of keeping the colors on the tops, I'm going to keep the colors on the fronts, and I'm only going to do it over 1 period. And then, well, this is just labeling the height so that I don't get confused. you just record what's at each height. So at this height, there's a red and a blue, which means there's a 0 and a 1 by my conventions. So you draw it. This height, there's a 2 and a 2, which is 2 1s. A 1 and a 2, well, and so on. And you put tensors between them, and you put dot, dot, dot to mean I could keep going up this wall. And this really is Kyoto path model. There's a little bit of being careful in that this is maybe in some sense the dual in that to make this crystal structure mapped up down here, the F's change a 2 to a 1, whereas you would normally say the F's change a 1 to a 2. So some symmetry happened. But other than that, it's the Kyoto path model with, well, with this particular perfect crystal. OK, good. So I would say we understand this relationship. Great. Now we are going to get into something new, or, well, not due to me, but due to Matt Fayers, which is we're going to define some new, different crystal operators, or well, operators. They're not always going to be crystal operators on partitions. So I've changed partition. Here's a partition. And I'm going to now tell you one different case of his crystal and then tell you how it generalizes. So the way this works is, again, to do F2, we're going to construct a string of brackets where there's an open bracket every time you can add and a closed bracket every time you remove. So these are the 5 places you can add or remove a 2 and still have a partition. But now I'm going to order them differently. And the way I'm going to order them is sort of lexicographically by height and then right to left. And the easiest way to draw this is to draw them as you're going to have to turn your head on the side to see the string of brackets. So this is the highest leftmost addable or removable 2. So I put a right bracket over here. This is the next one. I put a left bracket. Again, you cancel them, so it would add this one. This is, in some sense, a trivialized example. But anyway, so this is the rule. Why, I don't necessarily know, but it's a rule. And the theorem is that the component generated by the empty partition is a copy of B lambda 0. OK? Other components are not. And you can find counterexamples. I don't have one listed here. But I think even at about level 8, you start seeing things go wrong. I mean, you start seeing crystals that should be separate joining with arrows. And all kinds of horrible things happen. But the top component is fine. OK. Then you should always ask which partitions show up in here. And Matt gave a very nice answer. He said there should be no illegal hooks. Well, what's an illegal hook? In this case, it is just a hook in your partition that looks like this. So if you have an addable box on the left and a removable box on the right, they should be the same color. And I mean, I don't really mean addable, because it might not actually be addable in the partition. But the box that's missing here and the box that is here should be the same color. And they should be the same height. This is illegal. So all things that are, and it's in here exactly if there are no illegal hooks. Now, I cautiously say this means it's understood. And the reason I have cautiously in here is that if you really listen to what I just said, you have to check all hooks in the partition to tell whether they're illegal or not. There are n hooks, where n is the size. Is this really easier than trying to go to the top? Well, I think probably it's at least a little bit easier. I haven't tried to program it, so I don't know if it's actually that much easier. But maybe. And it's at least a good description in the sense that I can understand it. Because I can look at this, and I can wave my hands, and I can say there are no illegal hooks in there. And this actually is in B lambda 0. Whereas if I had to do the crystal operators, I would have crossed out boxes all over the page, and I would get confused. So for me, the whole thing, because the addable one is on the left. It has to be the addable one is on the right, and the removable one is on the left. So if this 2 was over here, it would be illegal. But if the 2 is over here, it's fine. OK, so what Matt says is you can actually do this in like really great generality. I chose to read this along horizontal lines and do lexicographically by height and along horizontal lines. But he says, why is nothing happening? Oh, yeah, I should point at that. The same result is true almost no matter what angle you choose, although defining illegal hook is a little bit more complicated. It's actually not very bad, but it's just a little bit more complicated than what I said. But nonetheless, you get, for any angle you choose to read, you get a different model for this b lambda 0. And that's uncountably many different models. I mean, any angle, eventually, you'll start reading things in different orders, and you will get something different. So, well, I found this both strange that there were so many models, but also good for me, because I already knew of 2 models. And then Chris Berg, one of Monica's students, had told me of a third one on these partitions. And having 3 models was upsetting to me, whereas having a whole family of models maybe is okay. So I will tell you how I knew of a second model on these partitions, more or less. Actually, I guess I never really proved this until after Fayer's results. But what I'm going to show is that this horizontal crystal is, in fact, very naturally the monomial realization of this b lambda 0. And the way the isomorphism works is that each inner corner in the partition you see corresponds to a y inverse for some I and k, and each outer corner corresponds to a y. So here's an inner corner. You look at what color a box here would be colored. It's 3. You look at the height of this inner corner. Well, you have to count up a little bit, but this is 11 high. So you put a y3, 11. Here's an outer corner. It's 2, and it's at height 12. So you put a y2, 12 inverse. Here's one at 2, I don't even know, 8. 1, 9 inverse. 2, I don't know. You just keep going. There's your crystal bijection. And proving, well, and then I guess this is not in the order it should be really, so you should change the order and stuff. And so this is your crystal bijection. And once you know to expect this, it's actually not very hard at all to prove. You notice that this 4 terms in the aik that you were multiplying by correspond to the 4 corners of the box you're adding. And sort of the ones on the diagonal where you're adding it get a negative, maybe? Yeah, negative, and the ones on the other diagonal get a positive. And you can just very explicitly see that the string of brackets I used here and the string of brackets I used here, well, they have the same brackets. And then you need to check the order is the same, and you start saying, well, it's not always the same, but the cases where it would be different are exactly when there are illegal hooks. The illegal hooks are exactly counting where the some order of 2 brackets somehow would change. And that's the proof. I'm not going to give more details than that. I think, yeah, I posted this to the archive just a week or 2 ago, and yeah. Ooh.
So the addable 3 was at height 11 and removable 2 was at height 12?
Yes.
But wait, isn't the 3 above the 2?
Yes, this is why the order of brackets would change. I mean, this could theoretically, I mean, normally I would count this as height 12 and this as height 11, because the center of this box is at height 11. Down here, I'm supposed to count this as height 11 and this as height 12. So if I had, I mean, this is exactly why if I had a removable followed by an addable, according to the crystal rule, I would read this first, but according to the monomial rule, I would read this first. However, I just told you this is exactly the definition of an illegal hook. So the definition of illegal hook is to compensate for the fact that when they do this monomial model, they read things at very slightly different heights. And I believe this, in some sense, works for other slopes. I've only really checked this carefully at this horizontal slope, but I think it probably works at other slopes in some sense. OK, so I assume I have. Well, as I've been saying you can do this at any slopes, and some other slopes correspond to known things. For instance, if I took this slope, well, this is very clearly the Mizuwa-Miwa model. I'm just reading from left to right. Although Thayer's actually doesn't allow us to use this slope for some reason. He puts this some bound. It's between something, and this is outside of the bound. But you notice that actually many different slopes would correspond to this Mizuwa-Miwa crystal. Because if I change this angle a little bit, I'm still just reading along the boundary of the partition. And as long as I'm just reading along the boundary of the partition from left to right, I'm going to see the Mizuwa-Miwa rule. And well, it's very obvious that you can go as far as having a slope like this and still get the Mizuwa-Miwa rule. But in fact, you can go all the way to this. And while some components would get messed up, the highest component, as long as there are no illegal hooks, you are still going to read things in the right way. And so this is what Thayer says, for some reason, how he sees the Mizuwa-Miwa crystal. Okay, and there's another one, which is due to Monica's student, and in fact, I think was the motivation for seeing all the other ones. And that's at this angle. So these were all known. So somehow we're interpolating between them, and I do not know. But I do feel better about the understanding of the relationship between, it bothered me that I couldn't see how this monomial crystal fit in with all these partition type models of crystals. And now we can say, well, there's this big family of partition models crystals, and the reason I can't see why this monomial crystal is matching with Mizuwa-Miwa crystal is it's a different point in this family. And you still might want to ask whether there's explicit bijections between the realizations at all different slopes, but then suddenly this isn't feeling like quite as natural a question to me. Well, this is where I got to. Anyway, I am just about done, so I think we're going to finish a little bit early, but I will finish with a couple questions that I would like to know the answers to. So these, one advantage I hope to see out of this is that, these Thayer's crystals, this is a purely combinatorial paper. He just writes down the rule, checks, and just checks it. And it's purely combinatorial. It's a reasonably long argument, and I don't find that there's any insight as to why this is true in the sense that there's no algebra behind it, there's no geometry behind it. What is there? However, these monomial crystals, there is some deep structure. There's Q characters, there's various things which I only partially understand. And the question is, can this help? And there is some positive evidence because, well, I mentioned before that there are modifications of this monomial crystal. And the one I'm talking about now is in a paper of Kashiwara called something like Realizations of Crystals, which was actually in the same collection that Nakajima's original paper on these was in, which was from a conference in Seoul. But this modified one does correspond with Mizuwa-Miwa crystal, and this was shown in a paper of Kim. So at least one instance of this family already does correspond to something known about the monomial crystal. We know a second one, so two instances of this correspond to the monomial crystal. It's some hope that other instances correspond to some modification of the monomial crystal. It would need to be modified in the sense that the definitions that are out there don't have enough freedom to have this many families, but I don't see why it couldn't be modified. Maybe there's people in the room who do. And then, of course, this is just an obvious question I'm always asking people and no one ever wants to answer because it's a lot of work. But these monomial crystals exist at higher levels. These JMMO crystals exist at higher levels. These, everything on both sides really exists at higher levels. So it seems like Thayer's crystals should also exist at higher levels in some sense. Haven't worked on this, but it's my hope. Okay, thank you.
There are about 20% of family names in Korea